good to go. Let's go. Is this working? Alright, I think we're good to go. So, hello everyone and welcome to our 30th programming challenge. It's a repeat, but this time we're going to be doing it a little bit differently and in a different language. So today we're going to be looking at a data structure called the B tree. And we did this a while ago in C++. However, I do want to refine that a little bit with memory-wise, and I also wanted to implement this in C so that we could actually use it in our C programs that we've been writing code for. So in combination with our C mathematics stuff, we're kind of aiming to write a program in C, and I wanted to kind of give us an opportunity to use the B tree, which is a really cool thing. So let me just, nope, not that. So episode 17 was when we last did it. Yeah, we did it in C++, and this time we're going to be doing it in C. So I'm currently just getting a few files ready. Just need to get the batch files created because I didn't do that. And then our header and source files. So yeah, we're just going to go through, do our hello world real quick, make sure that all works, and then we will go through the concepts. So in main.c, we're going to include btree.h, include standard IO, include standard lib, and include string. And then we'll have our int main, printf hello world, and then return 0. Am I still? I hope I'm not. I'm not muted. We're good. All right, and then for our batch files, I forget actually how to do this. Hold on. Let me try and find something real quick. No, that's not what I want. Alright, I think this is it. So GCC minus G. Yeah, so for our run, we just compile it with GCC, output it to a.exe, and input our source files of main.c and btree.c, and then call the executable. And then for debug, we simply add the debug tag, and then we also run the executable using GDB. Alright, so that's that. Okay, so let's hop into OneNote and let's go over a B tree and what it is. So I don't know what the B stands for. I don't know if it stands for anything, to be honest. But essentially, a B tree is very similar to a binary tree. And you see with the binary tree, we had that with our binary tree, we have, let's say, K1, K2, K3, and so on and so forth. Where all these K2s, so everything over here is, so this is all less than K1, and then everything on the right side of it is greater than K1. So if we were to kind of equate this to a number line, we would get that if we had K1 here, everything to the right side would be the child 2, which is this thing right here. C2 I'll call, and C1, which are both subtrees. So C1 contains all the keys that are less than K1, and all of C2 contains keys that are greater than K1, where we can use the big K as like our set of keys, which can be integers, real numbers, whatever you want to call it, anything that's comparable. Sorry, give me 2 seconds. My computer just went to sleep because I forgot to turn it on. I forgot to turn go to sleep off. Okay, very good. Alright, so yeah. Child 2 contains all the keys that are greater than K1, and then the first child contains all the keys that are less than K1. So one advantage of this is that it's automatically sorted, which is nice. However, iterating through it could be a little weird, or it won't be weird. It's pretty simple, but the thing is, it would take a while. It would be, you have to be comparing each key, and then you would have to recurse and do a child. And the height of this tree is it's log 2 of n. That's how many levels you have to recurse through to get to your key. Now, the B tree tries to be an extension of this with different parameters by extending the degree. So you can consider this binary tree a tree of degree 2. What a B tree is it's a B tree, it's a binary tree but with a degree m. So B tree has degree m. And what degree m means is that there's a maximum of m children on each node. So max m children on each node. And then also max m minus 1 keys on each node. And then there's also another constraint called the minimum constraint. So we have a min, which is just t is equal to the ceiling, the rounded up version of m over 2, this minus 1 number of children. And this is just a little side note here, except for the root node. And we'll look at what that means in a bit. Now, why did I say that this was kind of a more general version of a binary tree? If we look at a B tree of degree m, let's say, take for example m is equal to 5, then we'll have that you can have a maximum of 5 children. So m is equal to 5, therefore t is equal to 5 over 2, which is 2.5. You round that up, is 3 minus 1 is going to be 2. And let's just look at an example here. Alright, so I have 4 keys here, and I put them, so this is going to be a node. And we would call, right now, this would be a leaf node because there are no children in it. So that this is very similar to a binary tree where, let's say K2, this is going to be a leaf node because there's no children in it. And now when we want to make this, when we want to give it children, there are going to be, like I said, 5 children on a degree 5 binary tree. What that's going to look like is, this is going to point to C1. This will point to another child, C2. C3. C4. And then the 5th child, C5. And then all these children are nodes themselves. That's just how a tree works in computer science. So each child, let's say, has some amount of nodes, and it doesn't have to be full, which is also another cool thing about the B tree. With the binary tree, as soon as you insert a key, that node is full. You can't change it, or you can't like move anything around until unless you're deleting it. But here we have 5 children, and each of these children are going to be their own nodes with a set of keys and a set of children. Now, I said this was a degree 5 tree. However, that does not mean that each node has to have 4 keys. We could have a child, let's say child 5 isn't completely full. So we had 3 children, or 3 keys. So I'll say K5, K6, K7, and this was a node. This is a leaf node. This right here now, this is the root node. This is a leaf node. And then let's say C4 had 2 children, or had 2 keys, so it has 2 children. This becomes an internal node. That's just tree terminology. Now, how do we? Why is this B tree? Why is it structured like this? What's the advantage of doing it like this as opposed to a binary tree? Well, it's pretty much the same way that the binary tree sorts their keys. So we're going to equate this to a number line like we did with the binary tree. So if this is our B tree, we have our number line, I'll put like this, and let's put our 4 keys down. So we have K1, K2, K3, K4. I'm just going to renumber the example up here. Now, what are the children? How are the children sorted? Well, it's the exact same way, except now we just have more intervals. On this number line, we had 2 intervals. Less than K1, so the interval of negative infinity, let's just assume that there's integers here, so negative infinity, the smallest possible key, all the way to K1. And then the right side is K1 to positive infinity. That's 2 intervals. With a B tree, we now have intervals for each child, and that's going to be M intervals, the degree. So if we look at this number line, there are now 1, 2, 3, 4, 5 intervals. The leftmost interval is going to be negative infinity to K1. The interval between K1 and K2 is just going to be K1 to K2. Then we have K2 to K3, K3 to K4, and then K4 to infinity, positive infinity. And the way we equate these intervals is through the children, or the way we represent these intervals is through the children. So C1 has the leftmost interval, then we have C2, Then we have C3. And I'm just going to say this is C4 up here and C5 on the right. So C4, C5. Hold on, mine. Okay. So yeah. So every child is its own subtree, is its own sub-B tree. And every child contains a different range. So if we were to do, let's look at the interval for C4. So we'll go to a new number line here. Except this time we're going to bound our interval. So the root node is bounded from, it's just all it's the entire set of keys. So this is K. Let's say K is equal to the set of integers. I think that's Z, big Z. Could be wrong though. So K is just all integers. Now that's the root node for the root. Now for C4, we have a bounded interval, and this goes from K3 to K4. So any keys that C4, the root node of this, any keys that the fourth child and all of its children contains have to be within K3 and K4. So K3 is the left side is going to be inclusive, and the right side is going to be non-inclusive. So it's going to look like this. And then we're going to further divide these up into their own intervals based on C4's children. So we have two keys here, K5 and K6. I'll just put K5 here and K6 here. And then we'll sort of divide these up. So the interval from K3 to K5. The interval from K3 to K5 is covered by C6. Then K5 to K6. That interval is covered by C7, and then K6 to K4 is covered by the eighth child, or C8, this child right here. So you can see how these intervals are going to progressively get finer and more bounded, but then this is essentially how the B tree sorts and how it sorts its keys, essentially, and how we essentially make this work as a viable data structure. Bunch of bees. Or is that a lady? There's a ladybug on my window. There's two actually. It's kind of interesting. But yeah, so we're essentially just trying to figure out how to divide intervals into more finer intervals, and that's essentially how it's going to work. So let's look at an example on how this would work in this searching operation. So let's say, let's make a B tree with actual numbers this time. I think I have a picture somewhere of a nice B tree. Here we go, this is a good one. Oh, that's big. So this is an example of a B tree, and you could probably pick it apart right now, but this is going to be degree 4, or it at a minimum of degree 4. So, and I'm just going to say M from now on, but you can tell that it has a minimum degree of 4. Well, we can kind of figure out what the degree is because we have a maximum of 4. We only have we see a node with 4 children, the root node, 1, 2, 3, 4. So the degree has to be at least 4. So m is greater than or equal to 4. But then also we have a minimum. We see that there's a minimum of 3 children, but that doesn't really tell us anything else. We can't like determine a minimum bound here. There's enough. Are these even ladybugs? Because the third one just flew. I don't know if it flew. It might be a ladybug, I think. Yeah, there's 3 on my window. Okay. But yeah, so the degree has to be at least 4 here. Let's just say m is equal to 4. So let's look at the root node here real quick. Let's create a number line for the root node. And I'm going to make this really big so we can put all of our numbers on here. So our set of keys here is a set of integers. Or at least we'll say that for now. So we go negative infinity, or just, this is the k is equal to the set of integers. Let's look at our root. So we have 100, 155, and 226. So that's 3 keys. I will put 100 here, 155, and then 226. I'll actually just move these like that. So we have that. God, these fucking cars with their loud ass engines going by. So we have our key, or our first child, C1 will cover everything from negative infinity to 100. Child 2 will cover everything from 100 to 155. Child 3 will cover everything from 155 to 226. And then child 4 will cover everything greater than 226. So if we kind of drew a divider, that's going to be the first child, and that's its own subtree. That's the one thing that you guys, that's important to understand, that each one of these children are subtrees. We have another subtree, and then we have a third subtree over here. So we'll call this C1, C2, C3, and C4. So each of these subtrees have their own respective ranges on the keys that they can contain. So let's just zoom in on one of these real quick. Let's do child 2. So once again, in a child, in our subtree, we have a bounded range now. So this goes from 100 to 155. Left side is inclusive. Right side is exclusive. So we have in our child, in the highest node in our child, we have 128 and 140. So I'll put that over here, 128. And then 140. And then we'll say C21 for first child, C22 for second child, and C23 for the third child. And they will cover their respective ranges as well. And then So yeah, C21 will contain all the keys in between 100 and 128, so on and so forth. Now let's look at searching real quick. If we wanted to search for the key 117, how would we do that? Well, let's look at our number line. Essentially, that's what this tree reduces to. If we were to locate 117 on this number line right here, in the top number line for the root, we would have to go into C2. Reason why is because 117 falls into this range over here between 100 and 155. And then if we go further into C2, we see that we need to go into child 2-1, because 117 is in the range of 100, 128. And then if we go into C21, we'll see that we have two keys, 105 and 117. This time there are no ranges, it's only keys. So if we expanded this into a number line, we have a finer range here, bounded by 100 and 128, and we have our two keys of 105 and 117. And notice how I'm going to draw dots because it's no longer intervals, they're just discrete points. So we look at 117 and we iterate through the keys and we find that 117 is right there. So we have found our key. So essentially in the tree path here, we go to the second child and then we go to the first child and then we find the key. So that's how that works. All right, so let's start writing some code. We will go. I actually never tested to make sure that this works. Yep, all good. Okay, so we will go into btree.h, and we're going to start with some macros. So if not defined, btree.h. We're going to define btree.h and diff. And then we're going to want to define one macro, which is going to be our minimum possible degree. So define btree min m as 3. You could do 2. You know what, let's just do it as 2. Why not? And if you did it as 2, I believe it would just reduce to a binary tree. Because if you compare it to a binary tree, the minimum number of keys is 1, but also the maximum number of keys is m minus 1, so 2 minus 1, which is also 1. So there has to be one key in every node, which makes sense. Alright, so let's have our structure here for the node. So type def struct btree node. And in here we're going to have several values. We're going to have an integer n. This represents the number of key slots that are currently occupied. Integer number of children, the number of children that exist. This will be 0 if it's a leaf. So number of existing children. 0 if leaf. An integer pointer keys, so an array of keys. A void pointer value, a void double pointer value, so it's an array of void pointers, and these are just going to be the values associated with each key. So we'll sort by the keys, but you associate the keys with a value so that you can kind of sort the values by some sort of key, similar to a hash table or something like that, or any other tree, to be honest. So, and this is going to be a parallel array of values. And then we're going to have our children array. So struct btree node, and make sure this is a double pointer children. Alright, so that's our node structure, and now we're going to have a tree structure. So the way I kind of designed this was we're going to have a tree structure to contain the root node and the degrees, and then the node structures will contain the actual data and all the children and this tree structure itself. So we're going to have a type def struct btree, and in it we will have integer m for the degree, integer t for the minimum degree, and then a btree node pointer as the root. And then the way the B tree is going to work is we're just going to, the actual B tree structure is going to work is we're just going to pass it in with all the methods. All right, so let's start with just writing some constructors here. So for the B tree itself, we will have return type B tree new, and you're just going to pass in an integer degree. And then we will also have a void B tree free. And we will pass in a btree pointer b. And then for the btree node, we are going to do a btree node pointer return btree new node, and we're going to pass in the btree. And the reason why we're going to pass in the btree here is because the B-tree structure itself contains the information about how many children that we can have, which dictates how much memory we need to allocate to each pointer for the array. And then we'll also have a B-tree constructor that you can initialize by passing in a value. So new node item, pass in a B-tree, and you'll pass in an integer key and a void pointer value. So if you want to initialize a B-tree with a key and value. And then we will also have a free method which returns void. So void btree free takes in a btree node pointer root and a btree structure tree, because once again we need to determine how many children or how many keys that we have. Okay. All right, so for btree C, we're going to start by including btree, the header file. Then we'll also need standard io.h, include standard lib.h, include string.h, and then include math.h. We're only going to need math for one singular function. All right, so I'm going to copy over the signatures. And we'll start with btree new. We're simply going to determine if the bound is too small, so if the degree is too small. So if m is less than btree min m, then we're just going to set m to that minimum value. That's just a validation check. And then we're going to create the structure. So we're simply going to return. I'm going to use an initialized list. M will be m, the degree. The minimum will be the ceiling. This is why we need math.h. So, and make sure you're doing ceil float here. So ceil, C-E-I-L-F. We're going to pass in a float conversion of m divided by 2.0 float. And -1, so the ceiling value of that -1. And then pass in null as the value for the root. And is that it, or? No, not that. Okay, maybe it's not liking what I have here, so maybe I have to actually. Oh, you know what I think it is. We need to allocate the variable and then just return the variable. So move this initializer list to a btree variable called ret, and then we can just return ret. Yeah, that works. I guess you can return an initializer list that does not have a type yet. And then for btree free, we're simply going to call btree node free. Oh, I misnamed this function. The node free method should be btree node free. And we're simply going to call that method by passing in b.root and then b. Okay. Now for the node methods, we're going to start with the constructor. And then once we get to the free method, we'll look at some of the iteration techniques that we have, or just the one that we will use. So we first need to allocate a pointer. So btree node pointer ret is equal to malloc size of a btree node. Since we're dealing with arrays of pointers here, we need to be allocating pointers instead of just variables. So we need to allocate 3 arrays here. ret.children is equal to malloc tree.m times the size of a void pointer. I'm doing a void pointer because it's just an array of pointers here for the children. I could say btree node pointer, but they would both result to the same thing. Then we'll set all this to 0, so mem set. Does this actually matter though? I don't no, it actually doesn't. We don't need to do a set because we won't even be looking at it if the number is not high enough. So we allocate the children array, then we allocate the keys array, so ret.keys is equal to malloc. Now be careful about the number here. This should be tree.m minus 1. So remember, degree m means m children, but m minus 1 keys and values. So tree.m minus 1 times the size of an integer, and then ret.values is equal to malloc tree.m minus 1. That's the number of times the size of a void pointer. And then we'll set up our counters. So ret.n is equal to 0, ret.number of children is equal to 0, and then return ret. For new node with an item, we're simply going to call that method. So we'll allocate, so btree node pointer ret is equal to btree new node, pass in the tree, so we have just so we have a reference for the number of keys and shit that we need to allocate for. And then we're going to insert the value. So ret.keys at 0, make sure this is the first key, is equal to key. And ret.vals at 0 is equal to val. And then we need to increase the counter to 1. So ret.n is equal to 1. Ret.number of children is still 0 because we're just passing in the key and value. And then we can return ret. Alright, and then finally we have btree node free, and here we're going to look at the first way we're going to iterate. We first need to have a null pointer check, so if root, then we can clear stuff. Otherwise there's no values to clear, so we'll just get a bunch of memory errors. Okay. Red black tree. I could do a red black tree. That is true. I did AVL trees a little bit ago, which are similar to red black trees, but they're just a little different. Okay, so first check is just to make sure that the root actually exists. And then the first thing we're going to do is, or the goal in this method is to free all the anything that we called malloc on. So we have four things. We have the node itself, then we have our children array, the keys array, and then the values array. So we need to free those four things. So we'll start just with the arrays. So free root.keys, free root.values, and then free roots. And then for the children, well, why don't we just say free root.children? We can do that, right? Because we call malloc on children, so why not just do that? The difference is that we have an array of pointers. So the array is going to be freed, but all those pointers that existed as children are still pointers that are allocated, except we just destroyed our references to them, unless we had separate references. But if this node was the only thing referring to its children, which, for example, if we just had this root node and we call free on children, let me just copy this image real quick. So let's say that we called free on the root, free node on the root. Then we're going to free the array, the key and value array, and then we're also going to destroy the links in the children array, and then also just free the root itself. But all of these nodes are still here. So what we have to do is we have to do this as all other tree free methods do and make a recursive, or make the method recursive. So the first thing to do is we're gonna iterate through each of the children. So for integer I is equal to 0, I is less than root dot number of children, I plus plus. Then we're gonna call btree node free the same method, pass in root dot children at I, and tree as the new parameters. So we're gonna then move down. So before we free any of this now, so for free node root, we're first gonna go down to the left child, free the values, the keys and the values, destroy the node. It has no children, so we can't go any further. Then we're gonna go back up to the root, free this child, or not yet. We're going to go into this child here, the 128 and 140. Then we're going to go into its children, free those keys and values, destroy it. Go to the second child, free the key and value, destroy it. And then the third child, same thing, destroy it. And then once we've done all that, we're going to free these keys and values. Then we're going to destroy the links to the other nodes because they're pointing to garbage values now, but we're also just destroying the array, which is what we want. Then we're going to free the node, so on and so forth until we have destroyed all of our things. So this is a breadth first traversal, or sorry, a depth first traversal, where we go all the way down and then shoot back up. That's just how tree deletions work. So I'm just going to finish this real quick. Alright. Oh, no, not that. Then we free the root's links to its children, and then we get rid of the root, and then we're done. All the memory has been properly deallocated. Alright, so that's the basic stuff. Now let's go into our first operation, which is going to be searching. So we've already looked at how searching works. I'm just going to do our signatures real quick. So the way I'm going to structure this is we're going to have one method for the B tree structure that will call the specific method on the root node. So we'll say void pointer, so we're going to return a value associated with the key, with the integer key. So it's going to be btree search, pass in a btree tree and an integer key. And then for the node, it's going to be very similar. It's going to be a return type btree node pointer, btree node search. Excuse me. Sorry about that. I hope that didn't explode the microphone, but so the btree node search function will return a node and an index. So we'll pass in a btree node, which is the root, the btree tree, which will determine how many children or the degree. Actually, do we? Just wondering, do we need that actually? Huh. I don't think we need the tree for this one actually. Yeah, we don't need the tree for this, the search method. So the node search method will take in a root, an integer key to search for, and then an integer index pointer to return an index to. So we will write to this index here. And that's going to be the index of the child, or the index of the key in the return node. So if we find the key in root, we're going to return root, and then we'll also set the index to whatever index the key is at. All right, so let's copy our signatures over. So let's do the btree search one first. So we're first going to allocate an index, so integer idx. Then btree node pointer ret is equal to btree node search, and we're going to start the search at the root node, so tree.root, and then tree, or we don't need to pass in tree actually, we just pass in the key and a reference to idx for the index. And we're going to leave it for now, but we will look at it, what we're going to return in a second. For the actual btree node search function, this is going to be where we start learning about how to traverse through our btree. So we're going to start by looking through the keys, and we're going to compare the key to each of the keys. Or we're going to compare the input key to each of the keys that exist in the root node. So we're going to say for a dereference of idx is equal to 0, a dereference of idx is less than root.n, and then for the incremental step, we'll say a dereference for idx plus plus. And then in the for loop, we're going to say if key is equal to root.keys at the dereference of idx, so at the current index, then we're going to return the element. So return root. Is that good? That is not the whole story. However, because if you remember in our example, we were traversing down to children. We needed to refine the interval that we're searching through and go to the one further down below. So what we need to do is, instead of just iterating through each of the keys and comparing them, we need to iterating through each of the keys and comparing equality, we need to just compare the keys, period. So we're going to say, in a condition for the for loop, idx has to be less than root.n, and, make sure that's an and, key is greater than or equal to root.keys at the dereference of idx. Now, why this? So our first condition just makes sure that we're in the array bounds, but here we're determining if the key is still greater than root.keys. So for our example, we were looking for key 117. So we look at the first key in the root node, which is 100. That's right. So we want to go to the next key and compare it there. So 117 is greater than 100, go to the next key. 117 is less than 155. However, we know that 117 was greater than the previous key because we got to the 155. We're going left to right. So therefore, we want to actually just go into the child in between 100 and 155, which is just the one with the 128, 140, and then further on the 105 and 117. And then if it was the first one, so for example, in this child here, we have 128 and 40. We see that 117 isn't even greater than the first key, so we want to go down the leftmost child. So we're going to stop the iteration as soon as the key is less than the key, a key in the array. And then for the return statement, we're going to say return root.end. So if this root, root.number of children, sorry, question mark. So if there are children, then we can traverse down. So if we have children, then we're going to return btree node search. We're going to pass in root.children at the dereference of IDX. So we're going to go to the current index that we're looking at. And also note how the indices of the keys in the node are aligned with the indices of the children on the left hand side of that node. So the node at index 0, 100, C1 is at index 0 and C2 is at index 1. So if we start our counter at 0, we're going to compare the input key to the key at index 0, and if it's not greater, then we're going to go into child 0. So root.children at the dereference of IDX, and we're going to pass in the key, the same key, and then the index, which is still a pointer. And otherwise, we're going to return null. So this is simply just going to be, this is essentially saying if it's an internal node or the root node, traverse to the children if we have not found it. Okay, so that's that. Now for the btree search method, we have gotten the return node, and we also have the index of the key at that node. So if ret, because remember we can return null, if ret, we're going to, we can just say return if ret, then we have found a node, so we're going to return ret.vals at IDX. Otherwise, we're going to return null because we didn't find anything corresponding to the key. Okay, so that's searching. This is taking a lot longer than I thought it would, but okay. Now for the actual interesting part. We're going to do addition to a tree. Okay. Yeah. So let's go into OneNote and we will look at adding keys. So addition. Alright, let me find a good example. Or, you know what, we can just make it up. Alright, so when we add keys, it's going to be very similar to searching, in which we need to find the leaf node, or it's not going to be similar to searching. We're going to be sorry, it is going to be similar to searching. If we find a value, or if we find the key already in the tree, we're going to update it. So change its value to the passed in value. Otherwise, we're going to go try and find a root node, or a leaf node. So it's going to be very similar to a B tree insertion. That way, we're going to go all the way down, try and find it, and then, yeah. So we're going to try and find space for it, and then we'll insert it in order. So the first, so there are going to be a few cases here. First one is the tree does not exist. So the root does not exist. And for this, you're just going to create the root with a singular key. For now, I'm not going to be adding values, but just you can imagine that there are values attached to these that the node will point to with its value array. So let's say we wanted to add the value 17. So the root does not exist. We simply just add a 17. Like that. And let's say that for we have our m is equal to 3. So m of 3, and if we don't have a root, then we're simply just going to create the node as a root. Second one is going to be a leaf node without a violation. So leaf node without violation. Steps are going to be, and without violation I mean the degree, or the n, is less than m. So even if we add this node, it's still the degree is still going to be satisfied. That maximum number of children, there should be m minus 1. That maximum degree will still be satisfied. So leaf node without a violation. So let's say that we wanted to add the key 30. We would simply go 17, which already is there, and then just insert it in order. So we're going to look, is 30 greater than 17? No. Then we're going to go to the next one, but we've reached the end of the array, so we're just simply going to tag it on the end. And then we could also add, so at this point we have n is equal to 2, which is less than m, which is equal to m minus 1. However, before this, n was less than m minus 1. So n is equal to 1, which is less than m minus 1. So we have two children, or two keys in the node, and now we're going to do a leaf node with a violation. So for here, we have n is equal to m minus 1. So if we were to add this key simply like we do, we're just going to be increasing the degree by the degree is going to be increased beyond the maximum degree. So if we wanted to add the value 45, then we have 17, 30, and 45. and we simply, or sorry, this is wrong. If we were to add it without any care for the violation, we would just simply tag it on the end like we did with the 30, because we'd search. It's greater than 17, it's greater than 30, so we just tag it on the end. That's fine. However, n is now equal to 3, which is greater than m minus 1. M is the maximum number of children. So if we were to have children here, we would have 4. And that would violate the degree, or violate the condition. So what we have to do is we have to split this child up, or this node up. So we're going to split by bringing the median element up. So bring median up. So what this means is we're going to have the 17, the 30, and the 45, and the 30 is going to be brought up. And then the smaller keys become a node, become their own node, as the left child of the median, and the larger keys become their own node as the right child. So what this looks like is we have our 30, which is brought up, and then it has a left child of 17 and a right child of 45. Let's do a degree. Let's just look at the degrees. So we have n is equal to 1, good. N is equal to 1, good. And n is equal to 1. Also, note the structure here. All the keys to the left of the 30 are less than. So we have less than 30, and then greater than or equal to 30. So because we brought the median element up, which allows us to divide it up into two children of m minus 1 over 2, or m over 2 minus 1, so if we have degree 5 and m is 3, we're going to have t is equal to 3 over 2 minus 1, which is going to be 1. So we have two children that now satisfy the minimum key property. So we have n is equal to 1, which is equal to t. So we have enough keys to satisfy that minimum key property. So now we have a two-level B tree, and what you'll notice as we go further on is B trees are going to be built upwards. So when I said bring the median up, I literally meant bring the median up. That's just how the B tree works. You start at the leaf, where all the leaves are going to be at the same level on the ground, and then we're going to build upwards. So let me just illustrate this again. We had our 17, our 30, and the 45 on the ground, and then the 30 is brought up. So we have the 17 and the 45 on the ground with parents, with the parent 30, like that. And the way we're going to illustrate this in code is we're going to have a recursive method for insertion, just like we did for the search, because remember, we're essentially finding the leaf node where this node, or where this key would go, which is essentially searching. And we're going to return 30. 30 is going to be returned, this is going to be the return value of the method. And we're going to return it to the parent to be dealt with there. So we're going to be recursing upwards. I have both my windows shut, and I can still clearly hear engines. This is so annoying. Okay, so let's add a few more keys. So let's add a 20. So we have our 30, 17, 45. So the 20, we're going to compare it. We're going to look in here. We see that it's less than the 30, so we're going to go down the left side, the left child there, and we're going to tag it on. So we have the 30 as still as the root, and then all of our leaves are on the same level still. So the 17 and the 20 become are their own node. And then we have 45 as another one. Once again, if you wanted to do a degree analysis, we would have m is equal to 1 in the root, m is equal to 1 in the right child, and m is equal to 2 in the left child, which is still fine. Now let's do this again. Let's add... why don't we add a nice 25? So we have our 30. I'm just going to draw the tree. We actually just copy it. That didn't copy it. Like that. And if we wanted to add a 25, well, what we would do is we would look at our root node. We see that it's less than 30, so we're going to go down the left child, and we're just going to tag it on the end, right? Well, if we do a degree analysis, we'll find that n is equal to 3, which is greater than or equal to m, which is not what we want. So what we're going to do is we're going to split this node only up. We're going to split the 17, 20, 25 up. So what this is going to look like is we're going to have our 17, 20, 25, and we're going to send the 20 up. So we have our 20, 17, and 25. And this 20 is going to be returned to the parent. So we have our 30. Why does my laptop keep dropping connection? Uh-oh. Okay. Sorry, my laptop just dropped connection for a second. So we have our thing here with the keys. Oops. And as we recurse down, from the 30 to the 1725, when we return a value up, we're going to be essentially passing it back to the parent. So we're going to go back up to the 30, which is just the end of the recursive, the end of that recursive call. We're going to return to the root, and this 20 is going to be tagged on as if we were adding the 20 to the 30 node. So what we're going to do is we're going to have a 20 and a 30, and this doesn't violate the conditions. We'll look at what happens if it does. So n is equal to 2 here, which is good. But what do we do with the children? Because we now have two different children, a 17 and a 25. If this was a binary tree, we would simply just do the 30, which points to the 20, and then that points to the 17 and 25. The binary trees are built downwards. This tree is going to be built upwards, so we're passing along the 20 to the parent, but the 20 is going to take 2 new children with it, which are going to replace both the previous child. So this previous link right here is going to be replaced by this node right here. So we're going to have the 17 as that node, or as that child. And then in the middle, what's that child going to be? It's going to be the 25. So by passing up a node, or by passing up a key into the parent, we're creating room for one extra child because there's an extra interval to be covered. So we have the 17 and the 25, which are the first 2 children, and then the 45, which is going to be the third child. So now we have our root, which has two keys and 3 children. So n is equal to 2, and then we have all of our leaves. Notice that they are on the same level. So I'm going to do this a little quickly. Let's try adding... oops, no, not that. So let's try adding a 19, or let's add a 50. So we can simply just tag it on to the 45. That's pretty simple. Nothing has to be dealt for because no conditions were violated. And once again, that location is found by going to the 20. It's greater than the 20. Greater than the 30, so we go and we've reached the end of the key array, so we just insert it in the last child there, and that index that we look for at the end will match that last index of the child, and you'll see what I mean when we write the code. So we do a plus 50, that's good there, and then now what we want to do, so I'm going to copy this again, is let's add a 60. So we could tag it on. Once again, we would go over there, and then we would compare to the 45 and the 50. But this now violates our condition. We have n is equal to 3, which is greater than or equal to m. So what we have to do is we have to split it up. So the 50 goes upwards. So we have our 50. Left child is going to be 45, and the 60 is going to be the right child. And what we're going to do is we're going to, so I'm just representing the root node here is a 30, and we're going to return this 50 up the branch to the parent. So in the parent, we now have the 20, the 30, and the 50. And then our 17 and 25 children are the same. Now, the difference is we have created space for another child, which we can do. So which is good. We can add the 45 and the 60 as we did last time. So since we added a new key, we have space for 2 new children, one of which will just be the first half of the last node, or of the node that used to be there. So essentially, I'm writing, or I'm diagramming this as if you just removed that node completely when it needed to be split, and you can think of it like that. We're going to be removing the node, so this link right here will be destroyed. You can think of it like that. That's perfectly fine. So then when we add it, we're going to be adding the child. We're essentially going to be adding on this whole section. So this whole thing was this right here. So we're just tagging it on. So we have a 50 and then a 60. However, you'll see that the root node now violates our condition. So we have n is equal to 3 is greater than or equal to m. Now how do we deal with this? It's going to be the same exact thing. We're going to pop out the 30 and we're going to bring it up. The left child will be all the keys that are less than it. So that's the 20. And then 50 on the right side. Now what do we do with the children? This lends itself perfectly because we can just pass along the children to that. So we can simply just take the children that are left of the 30, move them to the left child, and then the children that are right of the 30 and move them to the right child. 17, 25, and then 50 will have the children of 45 and 60. Notice how the structure is preserved. All the keys on the left side, or that you can get to through the left subtree, are less than 30, and all the keys that you can get to through the right side are greater than 30, greater than or equal to 30. I think it's just gonna be. We will write it as just greater than. Okay. And once again, we pop up the 30 and we build upwards. These leaves are all on the same level. So we pop upwards. And then 30 becomes the new root. Alright, so we're going to write the code now. Quick note though, the way I was diagramming it, I was acting as if there was space to add that extra key. So you just tag along the extra key and then you split from there. However, we didn't allocate the memory for that. In the last time we did this, I allocated the arrays so that there would be an extra space so you could do the splitting pretty easily. But we're going to have to consider the way that having that finite memory changes things. Alright, so let's hop into Visual Studio Code once again. And we'll start in the header file. For the B tree method, it's just gonna be one. So we'll have return type void B tree insert, and we're gonna pass in a B tree pointer tree. So we want to pass in a pointer because we may be changing a few things about the tree. Like I said, in this, the root may change. The 30 became the new root. So when we pass in a pointer to a tree, we can actually change that root pointer in the memory and have that be reflected in the caller's copy of the tree object or the tree structure. So we're going to pass in a B tree pointer tree, and then also an integer key and a void pointer value that is the key and value pair. And then for the B tree node, we're going to have a few methods. There's going to be one utility method and then two methods that we're going to need to complete the insert. So the first one is just going to be a move value. So it's going to be void btree move key value, pass in a btree node pointer in, an integer in IDX, a btree node pointer out, and an integer out IDX. So we're simply taking a key value pair from the input node at the input IDX and outputting it to the output node at the output IDX. Those are the 4 parameters. So we can actually, well, let's just do the signatures and then we'll write everything. And then we're going to have 2 methods here. One's going to be, they're both going to return btree node pointers. First one's going to be a split one. So we're going to pass in btree node split. And this is going to take in a btree node pointer root, a btree tree, and then also we're going to pass in a new node, which is going to be kind of the node to be inserted. So we're going to pass in a btree node pointer node, or new node, to be inserted at integer I, at the index I. So this would be the equivalent of saying, all right, so the new node is going to be this right here, this 50, 45, 60. That's going to be the new node. And we want to insert it at index 2. That would be the I value. For this one right here, for the 2017-5, we want to insert it at index 0, because that was the return index that we had here. And then the actual node insert method will just return a btree node pointer btree node insert, pass in a btree node pointer root, a btree tree for the values, and then an integer key and then a void pointer value. All right, so we'll start with move key value because it's actually just 2 lines. We're simply just, once again, taking values from one node and putting it into another. So we're going to say out.keys at out IDX is equal to in.keys at in IDX. And then in dot or out dot vals at out IDX is equal to in dot vals at in IDX. So it's once again just copying the key and value over. We're going to need this when we want to shift keys to make space to insert values in order. All right, so let's now do the btree insert to cover the first case. So for btree insert, remember the first check that we had was if the root did not exist. So to check that, well, all we're going to say is if not tree dot root, then we're just going to say tree dot root is equal to btree new node item, and we're going to pass in the tree for the, or a dereference of the tree, sorry. Then the key and value will just be key and value. So we're going to create a node with one item, which will just be the passing key and value, and that's the new root. Otherwise, we're going to call it and pass it into a child. We're going to recurse down to the, or we're going to start the insertion method at the root. So btree ret, or btree node pointer ret is equal to btree node insert. We're going to start inserting at the root, so tree dot root. We're also going to pass in a dereference of the tree and then a key and value. Now, what I said about the return value of this method is if B tree node insert returns something, that is the equivalent of popping a node up. So when we looked at the 1745 and we added the 30, the median was popped up, and it's going to be returned as its own node, with the 30 as its key and a value. Kind of similar to how we just create a root here. So what we're going to do is, if we see a return value, we're going to update the root. So if ret, then we're going to say tree.root is equal to ret. Just like that. Because if the root is full, we're going to be building upwards. So if we add something to the root, we're going to split the root up into two children, and those two children will be those two new nodes will be the children of the returned parent. And that parent just becomes the highest level node, which will just be the root. So we just need to update the pointer to the root in the tree structure. So that is this case right here with the 1745, and then also the last one where we popped up the 30, like that. All right. So now, last two methods, we need to do the split and the insert. So we'll do insert first and then split. All right, for insert, this is going to make a little bit of sense, I hope. So the first one is going to be find a position. And we're going to iterate pretty much with how we did the search. So we're going to say integer I is equal to 0. Then while I is less than root.n and key, you know what, we can make this a for loop to make it more like the search method. So for integer I is equal to 0, I is less than root.n, and we're also going to add that second condition where the key has to be greater than or equal to. So I is less than root.n and key is greater than or equal to root.keys. Or, you know, let's just say key is greater than root.keys. No, it has to be greater than our. Okay, you know, we'll say keys greater than or equal to root dot keys at I. That's the second condition, and then the incremental step will be I++. And when that, we can just let that loop run. And then after the loop, like I said, if we insert a duplicate key, we want to replace the value. So if I is greater than 0 and key is equal to root.keys at I minus 1, then we want to replace the key. Sorry, I should be a method variable. So to replace the value rather, we're going to say root.vals at I minus 1 is equal to val, and that's that, and then we can just return because we don't need to do any further operations. I kind of want to make this a while loop just because it's not good practice to have an empty bodied for loop. So we're just going to replace this with an integer I is equal to 0 for the method, for the function, and then we're going to say while I is less than root.n and key is greater than root.keys. And while this is true, we're going to say I++. Or keys greater than root.keys at I. And then also that, okay, sorry. Delete the condition of replacing the value. We're just gonna look at the while loop. So we start the counter at 0, and then we go goes from 0 to root.n, or until we find that the key is less than or equal to a value. And then we want to check for the case that the key is equal to that value. So if key is equal to root.keys at I, then we just want to replace the value. So root.vals at I is equal to val, and then return. So that's good. Or sorry, this condition needs to be if I is less than n and key is equal to root, because, or if I is less than root.n, because this loop can also end when I is equal to root.n. So in order to have a valid index to check at it or replace, we need to have that I is less than n to be valid. All right, and so otherwise we did not find the key in this node. So now we need to determine what to do. So we're gonna have a placeholder, btree node pointer ret is equal to null. If not root.children, or not root.number of children rather, because children will always be a valid pointer. We just need to determine if there are any children, and if there are no children, it's a leaf node. And this would mean if it's a leaf node, then we want to just insert it into the leaf. And otherwise, we're going to insert it into a child. Now, after this if-else statement, we're going to return the ret, and it is going to be our job in this if-else block to populate this ret value if we need to pop anything up. So if we can insert it into a leaf node as is, good, that's good. We don't want to change anything. We don't want to pop anything up. Or insert it and not violate anything. We should do that because we don't want to violate anything. And then if we do need to pop something up, we're going to set that as the return variable and then return that to the parent, or to the tree for that matter. Okay. So let's start with the leaf node because it's the simplest. So if root.n is equal to tree.m minus 1, then we will have an overflow. So we need to split and upshift. So what we're going to say is return is going to be equal to root dot, that's just number of, no is number, it's, I could change that to number of num, but it's just the value in the structure here, and it just contains the number of children. So if root.n is equal to tree.m minus 1, we're going to have an overflow. So we need to split and upshift. The way to start this is we need to allocate memory for a node. So return is equal to btree new node item. And we're going to pass in the tree to get the degree and the allocation proper. And we're going to populate it with the key and the value that we're trying to insert. And then we're going to split the elements. So split elements. I actually did make a mistake, but we don't need to worry about it right now. It's just the return type of split. We'll figure that out when we write it. And then for split elements, we're simply going to say btree node split, what the parameters that we're gonna pass in. We want to split the root node using tree parameters, and the new node to insert before splitting is going to be return at index I. So we see how this works here. The parameters are root, which is just the current node, the tree, which just contains the values for the parameters. The return is our new node that we want to pass into insert, and we want to insert it at index I. Now split will take care of shifting the elements so that we can actually put in the node, and we'll worry about that when we write that method. And then otherwise, we can simply insert without a violation. And to do that, we're going to write shift elements after. So for integer j is equal to root dot n, j is greater than I, j plus plus. And in this case, we're going to say b tree, or for each iteration, we're going to say b tree You're welcome. That is fucking cool. You got a job at 11-Bit Studios. Good for you. That's fucking awesome. So for each iteration, we're going to say b tree move the key value. We're going to move from the root at j minus 1 to the root at j, because this is just how a right shift works. We count down, or this should be, the iteration step here should be j minus minus. So we start at the end of the array, and we want to move elements one index up. So we're going to be counting down. So root goes from, or we just essentially just shift at each element up by one index. And then we insert the element. So root.keys at I is equal to key, and then root.vals at I is equal to val. And then cannot forget, but we need to increase the counter, or increment the counter. So root.n plus plus. Okay. All right, now for the case where we have an insertion into the child, are we leaking Crow, don't lose your job at 11-Bit Studios if you're going to leak any information about any potential games. So for the internal node case, we want to insert it into the child. So once again, we're going to create a return node. Or do we want to? Oh, sorry, we don't need to create a return node. We're just going to insert this. We're going to call this method recursively. So ret is equal to btree node insert. We're going to call it on root.children at I. Oh, it was already announced. I am... forget I said that then. We pass in the root, the child, or root.children at I, because that's the index, or the range, the interval that we found that we want to insert it into. The tree will just be the tree, and then the key and value will be the same. So we're going to be recursively calling in the child, and then if ret has some value, so if ret, it's still confidential. You might get fired for this. You're leaking insider information here. So if the insert method returns something, then that means that some node popped up, as in either this case here where the 50 popped up, or in this case here where the 30 popped up, but some node popped up. That's just what happened. So if it did something, then we need to deal with that. However, there is the case where if we have an overflow in the internal node, then we need to deal with that accordingly. So if root.n is equal to tree.m minus 1, we will have an overflow in the internal node. So all we need to do here is just call btree node split on root, pass in the tree. The new node is ret, which will just be what we want to allocate to, because that will, what split will do is it's going to essentially create two new nodes. The root will stay as the root, and then we're going to have two new nodes to account for the left subchildren and the right subchildren. And then we can simply just pass in the pointer to take that popped up node that will be popped up. And we want to insert at index I, it is. How long did it take me to complete the open? Oh, that might be a question for Crowlag, but if you know C++, you're probably good. Like, because the series does go over a lot of the background. Like, not every video is just straight programming, but there's a lot of conceptual stuff in there too. So yeah, we can simply just call btree node split, and that will be enough for the overflow case for an internal node. Otherwise, we need to right shift the keys to insert the upshifted element. So to right shift, we're going to say for integer j is equal to root.n minus 1, j is greater than or equal to I, or sorry, this should be j is equal to root.n, j is greater than I, j minus minus. And here we're going to say btree move key value from root at j minus 1 to root at j. And then we're going to insert the upshifted element. And that's just going to be btree move key value. Now, the stored the key that it was upshifted is stored in ret right here, or where is it? This thing right here. So we're going to move the key value from ret at 0 to root at I, where we wanted to insert it, because we have right shifted to actually allow us to give us space. All right, and what we have to do now is we need to free the return value, because we have dealt with it. We've inserted all the values, or do we? Oh, sorry, not yet. Wait a second, don't do that. But because this is an internal node, we need to do the children. So right shift children. So for integer j is equal to root dot number of children, j is greater than I plus 1, j plus plus, or j minus minus, sorry. Then root dot children at j is equal to root dot children at j minus 1. And then we want to insert the children from the upshifted element. I don't know if we went over a specific example for this, but maybe we did. I think we did. Where was it? Right here. So when we popped up the 20 from this node right here, the 20 had 2 children, and we simply just took those children and appended them into the children list. So what we're going to say is root.children at I plus 1, because I plus 1 is the right child of a value. And then we're going to say root.children at j is equal to root.children at j minus 1. So root.children at I plus 1 is equal to ret.children at 1. And then root.children at I is equal to ret.children at 0. Now you're going to see the memory is going to be a little weird, or it's not going to be a little weird, but you'll see that there's going to be a bit of overlap in passing along children, because it turns out that ret.children at 0 is going to just be ret. Because the way we're going to do it is we're going to keep the left children in the original node, and we're going to allocate 2 new nodes, one for the popped up element and then the right child. So ret.children at 0 still refers to that node that was on, or the child that was on the left side, but just for completion or correctness, we're just going to set it so it's evident that we're doing it. And then now we can free the return. But we can't just call btree free node because it has pointers to the possible children and also keys. So what we want to do is we only want to free the arrays and not not recurse. So what we want to say is just free ret.keys, free ret.vals, and then free ret.children, and then free ret. And then also we want to set ret is equal to null, because this is still the ret that is in our method here that we want to pop up. However, if we don't violate any conditions, then we don't want to pop anything up. So the only way we're going to violate a condition is if n is equal to m minus 1. But in this else block, we're not violating anything. And then afterwards, we're just going to update the counters. So root.n++ and root.number of children ++. Okay. And then after the statements or the conditions about being a child or not, we're just going to return ret. And the only time ret would have a value is if root.n is equal to m minus 1, so if we're inserting into a full tree. And in both cases, so for the leaf case, we're going to set ret is equal to the new node item, but we're going to pass the new node item into split, and split will then pass along, or will replace that key value pair with whatever is going to be popped up. So after split will set ret to whatever's going to be passed upwards. And then similarly, in the internal node case, it's the same thing. All right, now let's do the split method. So I was mistaken, we don't need to have a return type, so btree node split can just be void. Can return void. Because once again, it's just going to set new node as the upshift element, and this allows us to avoid allocating too much memory. Alright, so the first thing we're going to do is we're just going to have some Boolean value to determine if we have children. And we're going to represent it as an integer, so integer has children is equal to root.number of children. And the reason why I'm allocating this variable here is because it's going to be a little cleaner to say if has children rather than if root.number of children every time. So we're just going to be allocating that memory there. And the reason why we can't do a character is because there may be a lot of fucking children in there, like more than 256. and there may be no bits that are active in the first 8 bits, so we just want to make sure that we get all the bits that are active. Okay, so we're first going to allocate a temporary node. So btree node temporary is equal to btree new node, and we're going to pass in the tree just to allocate memory, and then we're going to copy over the children. So memcopy tmp.children. That's the destination. The source is going to be new node dot children, and then the size will be 2 times the size of a btree node. So the maximum number of children that new node will have is just 2, because once again, we've either allocated just a single item, or I mean that's going to be the only time that we do. Well, new node will only be a singular item because we just want to input a single value into the space at index I. However, this value may be attached to 2 children, or it's either going to be a leaf, so attached to no children, or 2 children. But we don't need to worry about doing the mem copy here. If we don't need, if it's a leaf, this memory will still be valid. It's not like we haven't allocated the memory for the children. It's just, well, it's going to be, yeah, this is going to be valid. Okay, so now we want to swap the new node with the current, or with the node to be upshifted. So the way we're going to do that is we're simply just going to determine what would happen if we just put this node ignoring the array bounds. So to do that, we need to determine what would be shifted in order for this to be, in order for the new node to be inserted, and that's going to be determined based on the index that we're inserting out. So if I is less than tree.t, then we're going to insert before the median. What this will mean is the median element is going to be shifted. Or the current median. The current median element will be shifted. So what we're going to do is we're going to copy over the element that will become the median, and make that as the temporary value. So btree move key val, we're going to move from root tree.t -1, because the median is just the value at tree.t at that index, and we're doing -1 because it's going to be right shifted up to temporary at 0. And then what we want to do is we want to right shift to fill the gap of removing the median. So for integer j is equal to tree.t, I believe. Yeah, tree.t. What the fuck is going on outside? Jesus. I don't know if you guys can hear this, but this construction is going fucking crazy. So j is equal to tree.t -1. Hold on. No, this should be j is equal to tree.t. J is greater than I plus 1. J minus minus. And we're going to say btree move key value from root at j minus 1 to root at j. Is this right? This might not be right. Hold on. No, this should be j is equal to tree dot t minus 1, and then j is greater than I. Sorry. Because what we want to do is so let's say we had a tree of degree m is equal to 6. So t is equal to 6 over 2 minus 1, which is equal to 2. So if we had our 5 nodes, or our 5 keys, so K0, K1, K2, K3, K4, and we wanted to insert a K star, which was in the range of K0, K1. What this would result in is it would be K0. I'm just gonna remove the boxes, or just not draw the boxes in for now. Or I should probably. K0, K star, K1, K2, K3, K4. And then the median element will be K1, which is going to be popped up. So this becomes K1, which is the parent of K0 and K1 star. And then the right child will be K2, K3, K4. So we want to right shift everything, but this memory won't actually, this extra slot won't actually exist. So what this becomes in our code is, or we're going to define this in our code as copying K1 to temp. So temp is equal to K1. And then we're simply just going to move anything over that was before K1, or that was in between K star and K. Well, I mean, this isn't really the best example. Let's say that K star was in negative infinity to K0. Let's say that was that. So K1 still gets shifted up, but this time we need to right shift K0 to cover K1. So we need to allocate the manipulate the array so that we have space for K star in its slot. So this will become K star, and the only thing we need to right shift is going to be K0. And then K2, K3, and K4 will stay where they are. I'm an idiot. K1 is not the thing being shifted up. K2 is the thing being shifted up. Yeah, because that's the median. Right? Yeah, so K2 is going to be shifted up. So the left child will be greater than the right child after this. So temporary is going to be K2. And then we need to right shift so in this case I is going to be 0. So we need to right shift K0 and K1. I think that's, is that what I have to, I forgot what I have to find up here. But the thing is, I know that this code is supposedly works. Hold on. Oh, no. I was right the first time. K1 is the one being right shifted, or the one being popped. Because it's at index t minus 1. So we need to right shift K0 and that's it. And then after this, what we want the array to look like is this essentially. And then we'll divide it right there. Sorry about that confusion. So we right shift, j goes from tree.t minus 1 and that's to be greater than I, j minus minus, and we right shift. And then we want to insert the new node. So btree move key value. Now we're going to move from new node at 0 to root at I. So we've right shifted and created space for the key to be inserted at I. And then otherwise else if I is greater than tree.t, then we're going to insert after the median, and it's going to be pretty much the exact opposite. So what we're going to do is the current median element will be upshifted, will be popped up. So btree move key value root tree.t temporary and 0. Oh yes, okay. I've reason to this now. The element that's going to be popped up will be tree.t minus 1 because it will be at index t once we hypothetically inserted the new node. So when we right shift to create space, the key at index t will be the current key at index t minus 1. So that's why we start the right shifting at t. So btree move key value. So we go from tree.t, which will be, because if we insert it after the median, none of the median will not be shifted at all. So tree.t temporary 0, and then we're going to left shift to fill the gap of removing the median. So for integer j is equal to tree.t, j is less than I, and j is less than root.n, j plus plus, or this should be j is less than root.n minus 1. And we're going to say btree move key value from root at j plus 1 to root at j, and then we're going to insert the new value. So btree move key val from new node at 0 to root at I minus 1, because the position where this would be inserted is going to be left shifted after we pop up the median. And then finally, the last case will be the new node is the median. So new node will be popped. So in this case, we don't need to shift anything because we can just pass it straight up into the temporary. So btree move key value from new node at 0 to temporary at 0. Okay. Now after this, what we need to do is populate new node with the element to be upshifted, or to be popped. So btree move key value from temporary at 0 to new node at 0. Because at this point, we have inserted the new node value into the array, and we're just putting back the element that is now, or we're going to put the element, and the element that's going to be upshifted is in temporary. So we just want to copy it over to new node. Now we need to worry about children shift the children. So what we're going to say is new node dot children at 0 is equal to root. So the left child of the element to be popped is going to be the current root, because we're going to keep half the keys there. And next what we're going to say is new node dot children at 1 is equal to btree new node, and pass in tree just to allocate memory. So the memory that already exists containing the root children, this parameter, it already has children, and we just want to keep them there. We're going to take the right half of that children set, or the right half of those children, or of the keys, and put them into another node, which will be children at 1. Or sorry, this right here, this is not shifting the children, this is dividing the values. So what we want to say here is for integer j is equal to tree.t, j is less than tree.m minus 1, j plus plus. Then we're going to say btree move key value from root at j to new node dot children at 0, and then at index j minus tree dot t. So j minus tree dot t just resets the counter for the right child, just because we're copying from index j, which is non-zero to start. And this just essentially just gets all the right children. And then we want to set the memory to 0 in the root. So root dot values at j is equal to null. And we can also just, for completion, root dot keys at j is equal to integer max. Just so nothing will be greater than this key if we forget to do a counter, but that's not going to happen. So this is just for completion. And then now we want to shift the children, shift and divide children, just like in a divorce. Sorry if that hit anyone too close to home. Alright, so if has children, I guess you could consider a B tree like a polygamous relationship, just because there's multiple nodes. So there could be more than 2 nodes. So unless it's degree 3, in which case, yeah, that's not going to be good. Although I don't know if you want to equate this to a family. So if has children, and we need to do stuff. So if I is less than tree.t, we're going to do similar conditions. We want to copy the children to the right side. So for integer j is equal to tree.t, j is less than tree.m, j plus plus. Oops. So new node dot children at 1 dot children at j minus tree dot t is equal to new node dot children at 0 dot children at j minus 1. Because remember, new node dot children at 0 is the root, and the root while we did move over the keys and values to the second child, we still have the children there. So the new node we have to pass over the children. And then next thing we want to do is we want to right shift the children on the left side. And the reason why is because we're going to be passing in one extra, since we're inserting the new node with its children on the left subchild, we need to pop over one of those children. So, for example, if we had our keys and children, so K0, K1, I'll just do 0, 1, 2, 3, or 5, 10, 15. And then we had C0, C5, C10, C15, and C20. Why not? And if this violated, so let's say that we had an M is equal to 4, and this is our illustration of just inserting it so that we can split it easier. So the 5 would be popped up. So what we want is the 5 to be the top node, the 0, and then the 10 and 15. Like I said, this left child is still the root. As the parameter to split is the root. So what we need to do now is we still have all these children. So root has only the 0, but it has memory for all 3 children, or for all 3 keys. So it still contains, or for our illustration purposes, it still has all 5 children. So what we need to do is, or wait, no, this is that. It still has all 4 children. Or wait, no, I'm sorry. It still has all 5 children, just for our illustration purposes. So what we need to do is, we have nullified these 3 values, but we need to bring these 3 children. Let me see if I can do this properly. No way. So we need to bring these 3 children over to the right subchild, just like that, but only those 3 children. However, that was just the copying of the children. What's going to happen now is if we inserted on the left side here, we would need to put this node, or we would need to also move this node over like that, but that's not what happened. But yeah. So we have our 4 integer j is equal to tree.t, j is greater than I plus 1, j minus minus. Then new node dot children at 0 dot children at I plus 1 is equal to temporary dot children at at 1, sorry, wait, no, this is wrong. New node dot children at 0 dot children at j is equal to temporary dot children, or sorry, I was reading the wrong line. New node dot children at 0 dot children at j is equal to new node dot children at 0 dot children at j minus 1, just a simple right shift, and now we have created space to insert the temporary child. So new node dot children at 0 dot children at I plus 1 is equal to temporary dot children at 1. Sorry, this is a better explanation. That's not the root. That's not what we want. So let's say that the 0 was the thing that we inserted. Temporary, if you remember, we copied over the children. So temporary holds 0 and the left and right children of the 0. The left child of the 0 is already in place. But this right child, we haven't done anything with, or we shifted that over. So we need to allocate the space to, or we need to copy it over now. So that's what this is doing right here. And then else, because I'm only doing it in an else condition because the method for copying the children, if we're inserting on the right side or just popping the inserted element up, is going to be the same. So for else, we're going to say copy the children to the right side, as we did before. So for integer j is equal to tree.t plus 1, j is less than tree.m, j plus plus, new node dot children at 1 dot children at j dot tree dot t, or sorry, j minus tree dot t minus 1 is equal to new node dot children at 0 dot children at j. This is very clunky. But if we're inserting, the reason why we start the count at index t here is because if we're inserting below the median, then one of those children is going to be popped over to the right subchild. So here, we're going to say that we don't want to actually take that extra child because we're going to be copying only the children because the left subchild is not affected by this insertion. So that's why we start the count 1 after. And then we're going to right shift the children on the right side and not the left side, because this time in the other condition we were inserting on the left, here we're inserting on the right. So for integer j is equal to tree.t, j is greater than I minus tree.t, j minus minus. So we're going to say new node dot children at 1 dot children at j is equal to new node dot children at 1 dot children at j minus 1. That's just the right shift. And then we're going to insert the extra child on the left side. Or sorry, on the right side. So new node dot children at 1 dot children at I minus tree dot t is equal to tmp dot children at 1. All right, and then so those are the conditions, and then after this we can just update the counters. So new node dot children at 0 dot number of children is equal to tree dot t plus 1, and then new node dot children at 1 dot number of children is equal to tree dot m minus tree dot t. And that's just how the counts work. All right, and then after the big if condition about if has children, so we need to update the child counts. And then now we need to update the key counts. So new node dot children at 0 dot n is equal to tree dot t. New node dot children at 1 dot n is equal to tree dot m minus 1 minus tree dot t. The new node dot n is equal to 1 because the new node is going to be what we're popping up. So that's only going to have one node. And then new node dot number of children is equal to 2, and we don't need to return anything because this new node is a pointer, and in insert we're going to take that that new node and assign it to ret, which we will return if needed, or if we will insert it into the current internal node as we do over here. Alright, so these are the updated counts. And that should be it. Okay. So I'm just going to go through a quick test because I got to go in like a few minutes. I have class. So I'm going to go into main.c and I'm going to mock up a quick print method. So void print btree, pass in a btree node pointer root. Then we're just going to print out a parenthesis to indicate the start of a child, or of a node. Then we're going to do for integer I is equal to 0, I is less than root.n, I plus. We're going to print out all the children. So if root.number of children, then we're going to print out that btree recursively. So print btree root.children at I, and then we're going to print out the key. So printf %d root.keys at I, and then after this we need to print out the last child. So if root.number of children, because the loop only loops over until we get to n, but there's the number of children in there. So if root.number of children, then print btree on the last child. So root.children at root.n, which is number of children minus 1. Yo-Yo Man 3D, what's up? And then print the closing parenthesis. All right, so for our insert, you can play around with this. I'm just going to make sure that this works properly. So I'm going to take an example from somewhere. We're going to have an integer array, and it's going to be 1, 2, 3, 4, 5, 6, 7 keys long, and it's going to be 8, 9, 10, 11, 15, 20, and then 17. And we're simply going to say for integer I is equal to 0, I is less than 7, I plus. And then we also need to instantiate our btree. So we're going to have a btree tree is equal to btree new of degree 3. Yeah, 3. And then in the for loop, we're simply going to say btree insert, pass in a reference to tree, elements at I is the key, and then we'll just have null for the value. Then I'm going to print out the element that we're inserting, so plus. Or sorry, this should be keys at I. And then print the btree. And then print out a new line. And then we'll free the btree. Okay. So that was just a quick mock-up. Let's run this. And it's not working. Okay. What's up? Return with no value. Oh, okay. All right. So in btree.c, remember where we used integer max to replace a key? This thing right here. When we were moving keys over to the right side, we need to include limits for that. So include limits.h. And then in insert, apparently I didn't return ret. And I did. Return with no value. Okay. In btree insert, btree node insert, when we replace the value, we want to say return null and not just return. Because if we return something, it might give a garbage value, which might mean, oh, it returned a node. We need to upshift something. So now let's run. That's not right. Okay. So we see that the 8 and 9 were inserted properly. The 8 and 9. Hold on. This is certainly not right. What the fuck happened? Okay, I don't think it's copying the keys over to the right side properly. So we need to go back to btree split. Alright, so it has children, temporary. So if I is less than tree.t, we want to move the key value from root at t-1 to temporary at 0, and then right shift to fill the gap. So we go j is equal to t-1, j is greater than I, j minus minus, good. And then move from j-1 to j. Then we want to insert new node at 0, root I. If I is greater than t, then we're inserting after the median, so the current median will be popped up. So move the key value from root at t to temporary at 0. And then j goes from t, and j has to be less than I and n minus 1, j plus plus. And then we move the value from j plus 1 to j, left shifting, and then we want to insert the new node. So new node at 0 to root at I minus 1. Otherwise the new node is popped. Alright, so if has children, if I is less than tree.t, then we want to copy the children to the right side. So j is equal to t, j is less than m, j plus plus, new node dot children at 1. Wait, did we... Oh, I need to look at this loop first. J equals t goes to t m minus 1, j plus plus. J goes to m minus 1, j plus plus, root, j. Oh, I'm an idiot. Move key value when we're dividing up the values needs to output to children at 1. Okay. And this should work now. So yeah, we're outputting to the right side, not the left side. So it was just printing out garbage values. And this not right? Or is it? No, I think this is right. Oh, it is right. So we have everything's in order. 8, 9, let me just zoom in a little bit for you guys. So we have 8, 9, 10, 11, 15, 17, 20. I'm using the, hold on. I'm using this example over here. So we do that 8. So we add the 8. The 8 and 9 you see are added as just leaves, which is good. And then we have add the 10, which needs to pop up the 9. So that's good there. Add the 11 goes onto the right side, 10, 11 there. Then we add the 15. 15 creates an overflow, so we need to pop up the 11. And you see that the 9 and 11 are on the same level. These two are on the same level. So we have 9, 11, 15, or 9, 11 as the root node keys, and then 8, 10, 15 as their children. And then we add the 20, which is just added to the right side. And then when we add the 17, what happens is the 17 creates an overflow in both levels. So we pop up the 17 to the root, but the root is now overflowing, so we need to pop up the 11. And that creates an 11 as a root node. And that has 2 subchildren, which are just like that. So yeah, I'm pretty sure this works. That was the one line of code that got fucked up, but it's good for now. Alright, I have to go to class. I have class in a few minutes. So, yeah, this was our B-tree insertion. Next time we will be doing B-tree deletion, which is going to be very difficult. Or not very difficult. This was 2.5 hours, motherfucker. Holy shit. Okay, so yeah, alright, I'll see you guys next time. Enjoy yourselves. And yeah, have a good one.
Thank you.